Okay, so now let's take a look at this next example. Well, now we have two different differential equations. So I've got one differential equation, dy dt is 2 minus y. So notice the independent variable has now changed to t. And over here we have dy dt is t divided by y. So this differential equation, because it doesn't depend on the independent variable t, is autonomous. This differential equation does depend on t, so it is not autonomous. And if we want to match each of these differential equations to one of these possible slope fields down below, we just solved it, right? Because this differential equation is autonomous. Its corresponding slope field should have the property that the slopes of the line segments are parallel, they're the same for the same fixed y value. So each time I move across a horizontal line on this slope field, we can see that all of the line segments have the same slope. So that's a good reason for this autonomous differential equation to match the slope field on the left. This differential equation, it does depend on the independent variable, and now we can see as we move through this slope field, the line segments are changing their slope both when we change t. So over here, if we fix a y value when we change t, these slopes are changing. When I fix a t value and move down a vertical line, we can see that for a fixed t value when we change y, the slopes are also changing. So because this differential equation depends on t and y, we're seeing that the slopes in the slope field are changing when we change both y and t. So by that process, we've matched up each of the differential equations with one of the slope fields. And then, just like in the previous example, what these slope fields allow us to do is get a good sense of what the graphs of the solutions look like, even if we haven't thought about what the formulas for the solutions are. We at least can sketch graphs for these solutions. So for example, when y is 0, when y is 1 and t is 0, so maybe that's about over here, this differential equation, the solution to that differential equation is going to have a graph which is approximately that shape. When y is 3 and t is 1, that's somewhere between here and here. And so that differential equation is going to have a solution that looks like that more or less through that point. And we can do this as well when y is 0 and t is 1. Maybe that's about over here. I can follow these line segments. And we can do the same for this slightly more complicated slope field on the right. That is when y is 1 and t is 0. Maybe that's about here. We get a good idea of what the shape of that solution is going to look like. When y is 3 and t is 1, maybe that looks like this. And when y is 0 and t is 1, we can sketch this solution like that. So here I'm just giving a kind of general approximation for these solutions. And one last thing that I want to comment on is we could have matched these up using some other properties of the equations for the differential equations and the properties of the slope field. So for example, for this differential equation, we can see that when y is bigger than 2, dy dt would be negative. And so we can see that for any y value above 2, all of the line segments here have negative slope. And when y is less than 2, all of the line segments have a positive slope. And we can't really see it, but when y is exactly equal to 2, we are getting that the slope dy dt should be 0. So we would have a bunch of horizontal line segments through any point that has a y-coordinate of 2. And we've got properties for this equation over here, namely that at any point when t is equal to y, so for example on the line y equals t, all of these slopes are 1. When t and y are same magnitude but differ in sign, then we can see that these slopes are going to be exactly -1. So there are other properties of the equations that we can check to see that they're represented in the slope field as well.